Welcome to the class, students. Uh, we have in the past session we have discussed what continuity is, how continuity can be checked at a point, how it can be checked in an interval. Today we will learn some of the important results from continuity. We will discuss algebra of continuous function and some important points to be kept in mind. Okay, talking about algebra of continuous function, say we have two functions f and g which are real valued functions and they are continuous at a real number c. Okay, that means f is continuous at the real number c as well as g is continuous at the real number c. So if this is the condition, then the sum of these two functions, their difference and their product will also be continuous at c. Even f divided by g will be continuous at c, provided the function g at the point c should not be equal to 0. Okay. Then there are various functions we have done in our previous class. Let us see how they behave. What can we talk about their continuity for the real numbers? You will find polynomial functions are everywhere continuous. No matter what real number the variable is, at that point the polynomial function will be continuous. In the same manner, sine and cosine functions are everywhere continuous. You can recall the graph of sine and cosine function. You will see we are able to plot the graph of both these functions without lifting our hand. That is because they are everywhere continuous. But when we talk about tangent, cotangent, secant, cosecant functions, these remaining four trigonometric ratios or functions, we can say, you must have seen they are continuous within their domain. If we are talking about their domain, we will be able to plot the curve without lifting our hand. Okay, so within the domain these functions are continuous. Same way logarithmic, exponential and rational functions are continuous in their domain. So rational functions, whenever we will be defining, it means we are defining it in its domain. Okay, same with the other functions as well. Okay, next is, if there are two continuous function, then their composition will also be a continuous function. We have done composition of functions in the chapter relations and functions. So if f and g are two such functions that their composition, say composition of f and g is possible and f and g are separately continuous at a particular point, then the composition of f and g will also be a continuous function. That is what it explains. Now let us try to attempt some questions from the exercise. See the first one. We have to prove that the function fx, which is defined as 5x minus 3, is continuous for x is equal to 0, minus 3 and 5. We are not going to check the continuity at these points. Instead, we will see the nature of the function fx. Okay, if you see carefully, fx is a polynomial function. And just now we have discussed polynomial functions are everywhere continuous. So we can simply mention as fx is a polynomial function, hence it is everywhere continuous. Hence it is everywhere continuous. Okay, so if it is everywhere continuous, then because we have to check the continuity at 0, minus 3 and 5, so we can directly write, therefore fx is continuous at x is equal to 0, minus 3 and 5. We are not checking the continuity at these points. Just by the nature of the function, we can conclude whether the function is continuous or not. Now look at these two parts of question number 3. Again, we are examining the continuity of the function. Just now I told you that if a rational function is defined, it will be always defined in its domain. So obviously over here x is not equal to 5. Because for x is equal to 5, the denominator will become 0 and we cannot define this function. Okay, so but if it is defined, that means it is defined in its domain. So we can again simply give the justification as fx is a rational function which is continuous in its domain, which is always continuous in its domain, hence fx is domain, fx is continuous. Fine, hence fx is continuous. So no point of discontinuity here. Okay, check for the next one. Next, see the nature of the function. It is a modulus function if you see. Now modulus function, even if you use the definition of modulus and expand it, you will find fx comes out to be a polynomial function. And if it is a polynomial function, it is to be continuous. Or you can even write straight away as modulus function are everywhere continuous because they give us polynomial functions. Okay, as modulus functions are everywhere continuous, hence fx is continuous. They are everywhere continuous, hence fx is continuous. So you can see the three examples we have done till now. Because of the nature of the function, we could not find any point of discontinuity for these three functions. Okay, let us try change the nature of the function now and check, can we find some point of discontinuity for it or not. Look at this function. F is defined in two ways. They are saying for x less than equal to 1, fx is x, and for x greater than 1, it is 5. So we have to check whether it is continuous at 0 and whether it is continuous at 1 or not. So first we will check for 0. Okay, so for x is equal to 0, we will first see how the function is defined for x is equal to 0. 0 is less than 1, and every time x is less than 1, fx is to be taken as x. So for x is equal to 0, fx is x. And what is the nature of function? Polynomial function. And if it is polynomial function, what can you say about its continuity? We know polynomial functions are everywhere continuous. So therefore, we can say fx is continuous at 0. So for 0 we have checked. Now let us find for x is equal to 1. Now if the function has to be continuous at 1, then the limit on the left of 1, on the right of 1, and the value of function at 1 should be same. Then only it will be continuous. If you prove any two of them are not coming out to be same, then it becomes a discontinuous function. So we will quickly check for value of the function at 1. What is the function at 1? Look at this definition. It says when x is equal to 1, fx is to be taken as x. So if fx is x and you are replacing x by 1, then f1 becomes 1 only. Okay. And what about the right hand limit? If you see the right hand limit, on the right of 1, check the nature of the function. It says when x is greater than 1, fx will be equal to 5. So on the right of 1, fx is coming 5. You can see it is not same as the value of the function at 1. So we have already shown two of the required conditions are not coming out to be same. Okay, so therefore fx is discontinuous at x is equal to 1. So 0 is the point of continuity, but 1 is the point of discontinuity. Okay, taking some more of the same type. Now in the coming questions, we will find all the points of discontinuity for the function defined in this manner. So when they say find all the points of discontinuity, so we are checking for all real numbers. Now you look at the function, read it thoroughly. It says when x is strictly less than 2, fx will be 2x plus 3. That means a polynomial function. For x strictly greater than 2, fx is 2x minus 3. That is also a polynomial function. So what do we know? We know very well for x strictly greater than 2 and x strictly less than 2. The nature of function is a polynomial function. Fx is a polynomial function and hence continuous. It is a polynomial function, therefore continuous. See, this we are talking about x less than 2 and x greater than 2. What about x is equal to 2? That may be a point of discontinuity. So we need to check the continuity at 2. I will see what the function is when x is 2. See, when x is 2, we need to use this definition of the function. It will be twice of 2 plus 3, that is 2 into 2, 4 plus 3, that is 7. You will see the left hand limit will also come out to be same. Okay, we can write also limit x tending to 2 from the left fx will be equal to 7, because for x less than 2 also we have to use the same definition. So we simply replace x by 2, it comes out to be 7. So value of the function at 2 is 7. On the left of 2 also fx is 7. Let us see the right hand limit. On the right of 2, the function fx is defined as 2x minus 3. So 2x, so I will replace x by 2 again. So what do we see? 2 into 2 is 4 minus 3, which comes out to be 1, which is not equal to the value of the function at 2, or which is not equal to the left hand limit. So therefore we can say fx is discontinuous at x is equal to 2. So for this particular problem, x is equal to 2 is the point of discontinuity. For rest of the real numbers, it is continuous. Fine. Let us see this one. If you see over here, a modulus is being involved. So I will quickly write it in a simplified form, then we will proceed with the question. Okay, see here, we can write it as, you can see the nature of x, it is less than minus 3. So obviously it is less than 0. And if x is less than 0, we write mod of x as minus x. So it will become minus x plus 3 for x less than equal to minus 3. It is minus 2x for x greater than minus 3 but less than 3. It is 6x plus 2 for x greater than equal to 3. Now you look at the possible points for which it can be discontinuous. You will find minus 3 and 3 can be the possible points of discontinuity. What about the rest of the points? So we can justify for them. You can see for all x, let us say less than minus 3, x greater than minus 3 but less than 3, and x strictly greater than 3. So I'm not including minus 3 and not including 3. I'm talking about values less than minus 3, values between minus 3 and 3, and the values greater than 3. For each of these values of x, or you can say for all these real numbers, fx is defining one of the polynomial function. So for all these, fx being polynomial is continuous. Being polynomial function is continuous. So we know that if x is one of these numbers which are mentioned here, then it will be continuous. I have only not included minus 3 and plus 3. So first we will check continuity at minus 3, then we will be checking the continuity at 3. So let us find the left hand limit at minus 3. So limit x tending to minus 3 from left. Look at this part. When fx is less than minus 3, the function is defined as minus x plus 3. If I replace x by minus 3, it will become minus of minus 3 and then plus 3. So minus of minus 3 is plus 3 and plus 3, that is 6. Okay. In the same manner, the value of the function at minus 3, for that also we have to use this definition of the function. So what is x to be replaced with? It is to be replaced with minus 3. So minus of minus 3 plus 3, which is equal to 6. So you can find they both are equal. And the right hand limit will be limit x tending to minus 3 from the right side. So you see what is fx on the right of minus 3. Look at this part here, x is greater than minus 3 and function is defined as minus of 2x. So this is the function on the right of minus 3. So what we are going to do, minus 2 into x is to be replaced by 3. So this is coming out to be minus 6. So this is not equal to the value of the function at minus 3. So what do we find here? For minus 3, all the 3 required conditions are not coming equal. So it is discontinuous at minus 3. Okay, let us check it at 3. At x is equal to 3, the left hand limit will be limit x tending to 3 from the left. So you check what is the function on the left of 3. Here we have the function on the left of 3. See, it says x is less than 3. So the function is to be taken as minus 2x. Okay, replacing, 1 minute. Please check this part. Over here x was approaching minus 3 from the right. So here x does not gets replaced by plus 3 but minus 3. So this is plus 6. Okay. So obviously this is not over here. Let me remove it. Please cut it down. So this is equal to f at minus 3, which is further equal to the left hand limit. So all three are equal. Sorry for incorrect substitution. You can see all the three are equal. So the function is continuous at minus 3. Okay, make this correction. Now checking for left hand limit at 3. So here x is approaching 3 from the left. So in this case I will replace x by 3. So this becomes minus 6. Fine. And what is the function at 3? Function at 3. See, when x is equal to 3, function is to be taken as 6x plus 2. So 6 into 3 plus 2. How much it is becoming? 6 into 3, 18. 18 plus 2, 20. So see, I don't have to check the right hand limit because here only we have shown it is not equal to the left hand limit. So at 3 the function is not continuous, but at minus 3 it is continuous. So therefore, because the question says you check the points where it is discontinuous. So 3 is the only point of discontinuity. We can write fx is discontinuous at x is equal to 3. So mentioning only the point of discontinuity because that is what the question asks for. At minus 3 it is becoming continuous. Okay. One more quickly let us take. See, this one we will be able to do just by using the definition of modulus function. No calculation is required. Let us redefine the function. Fx is x divided by mod of x when x is less than 0. So you quickly recall how do we write mod of x when x is less than 0. When x is less than 0, we write mod of x as minus x. So it reduces to minus 1 and the condition is x is less than 0. And what is the second part? It says when x is greater than equal to 0, fx is already minus 1. So look at all these. What is left hand limit? It is minus 1. It means limit x tending to about 0 we are checking. On the left of 0, fx is minus 1. Then see at 0, fx is minus 1. Right hand limit, limit x tending to 0 from right fx. So on the right of 0, here x is greater than 0. There also it is minus 1. You can see all three are equal. So this is same as the value of function at 0. It is same as the left-hand limit. So 0 is not a point of discontinuity. Fx is continuous at 0. What about the remaining